Hi, Margaret. I met with my students, so I'm going to do some more of the questions you sent me under like concept test 5.3. There's like 4 quick questions. It seems like these all have to do with density, and density, as you know, is mass over volume. Well, this chapter takes that concept that you learned a few weeks ago and it turns it into the ideal gas law to see what pops out. In order to connect the ideal gas law to the density law, you can see there's no mass inside the ideal gas law. But if you remember what moles is, which is the mass of something divided by its molar mass, you could derive a new equation. So why don't I take the ideal gas law here and substitute in mass over molar mass times RT, and then since I know what density is, I'll rearrange this to have the density all on one side. So I'll have pressure times molar mass divided by RT is equal to the mass of a gas divided by its volume, and that's what the density is. All right, the first question says, which of these gases has the highest density if they have the same conditions? So, same conditions. And so in order to answer this, you have to ask yourself, well, what's different about these gases? Ammonia, oxygen, xenon, and helium. Well, one thing about them is that if you have 1 mole, they all weigh different amounts. They have different molar masses. And if you look at this equation up here that we calculated density, you can see that the molar mass is proportional to density. In other words, if the molar mass goes up, the density goes up. So whichever of these gases has the highest molar mass, that's the one with the highest density. And so xenon, I don't have my periodic table right in front of me, but I'm going to look for it right now. Oh my gosh, xenon's not even close. Xenon is 131, helium is 4, oxygen gas is 32 because you have 2 of them, and then ammonia is 17. So the highest density is definitely going to be xenon because its molar mass is high, and that makes its density high. Question 2, or B, that one's B, I think also has to do with density. How does the density depend on the following parameters? So it mentions P, T, and M. So I'm going to rewrite this here. Pressure, molar mass over RT is equal to density. And remember, density is the same as mass over volume. So hey, I'm going to go to a different color just to do this and look at what happens to pressure. Well, pressure is in the numerator. So if pressure goes up, density goes up. If pressure goes down, density goes down. Temperature is in the bottom. So if temperature goes up, that means the density will go down because it's in the denominator. So pressure is directly proportional. Temperature is inversely proportional. And the final one is molar mass. I called it MM, but your book calls it capital M. If the molar mass goes up, then the density goes up because it's in the numerator. So molar mass goes up. And according to this problem set, it looks like B is the correct answer. So directly related is pressure and molar mass, and temperature is inversely proportional. When it goes up, the density goes down. Let's do a couple more. Concept test 5.3C, 44.0 grams of a gas at STP occupies 22.4 liters. Hey, that sounds familiar. The gas could be O2, N2, CO2, He2, or AR, argon. This one goes back to your memory. What does 22.4 liters mean to you? That means you have 1 mole of gas at STP. So basically, it's just a clever way of asking which of these gases is 1 mole for 44 grams. And the answer is CO2, is about 44 grams per mole. O2 is, 32, N2 is 28, helium is 4, argon is 40. And finally, 5.4 D, it says, what happens if you have a sealed flask, I'm a terrible drawer, But if you have some gas molecules in there and you increase the temperature, what happens to the density? Well, the density from the last slide is the mass of something over the volume of something. Since this says it's a sealed flask, it's not like a hot air balloon. Since it's a sealed flask, you're not changing the volume of the gas, you're not changing the mass. So I think the answer is C, remains the same. Again, if any of this doesn't make sense to you, please give me a call. Bye-bye.